Hello, this is Larry Landis with Lattice Semiconductor. And in today's session, we'll be talking about our Avant FPGAs. And here we go. So a little bit about myself. I'm our product line manager for our general purpose products here at Lattice. My background is a combination of ASIC and FPGA designs. I've done design, I've done FAE applications and marketing. And as you can see from my bio, I have a really keen interest in teaching digital electronics. So I've taught as an adjunct at UC Berkeley, Santa Clara, and also Cal State University in Sacramento. And I also serve as an industry advisory role for a number of universities. Let me turn it over to my colleague Mario, who will discuss his biography here.
Hello, everybody. I'm Mario Villa. I'm CTO and founder of DP Control Italy. My background also is coming from academia. I was involved in many high-performance computing design all over my academic career, and I was a lecturer in robotics and computer vision for 10 years at the University of Salerno, where I earned my master and PhD degrees. Since 2016, I was serving as a full-time chief scientist first and CTO of the whole TTM group in Italy, which is a group of companies totally devoted into technology, FPGA design, visual architecture, and all what regards the technical developments around imaging and video. In 2020, our companies also have been involved into another round of big investments from another technological company, and I'm serving as a CTO of the whole group since then. DP Control, the company I'm representing and that I founded in 2002, it's a company which has a strong background in imaging and can serve as a provider for imaging technologies in many of the different verticals areas.
Thanks, Mario. Appreciate that. Okay, so today we'll talk about some of the current FPGA design challenges. We'll have a short discussion on our Avant mid-range FPGA platform. And then we'll turn it over to Mario, who will discuss his project called Tarantula. And one of the great things about Tarantula is Mario is one of the very earliest users of our Avant product, and we'll be able to describe not only the product, but some of the design challenges and techniques that he's used to use the Avant product. So if you look at the overall industry, one of the great things about being in FPGAs is it just continues to have a great growth rate, nearly 10% year on year if you look over the long history of FPGAs. And what Lattice was finding, our concentration has historically been in the small FPGA space, and this tends to be FPGAs up to 100 to 150 four-input lookup tables. And we were looking at growth areas and listening to our customers, and what we were finding is lots of edge AI, lots of small form factor, lower power needs are needed for the next generation of larger FPGAs. So in that, we started setting out a path to come up with the right blend of features, power, performance, and packaging options for our Avant family. So one of the things that our customers are telling us is the huge increase in cameras at the edge. Lots of edge AI applications are out there. Transition that we've seen in our ever dropping cost of home TVs from HD to 4K, and multi-sensor systems, which will be demonstrated in the DP Control solution, and in other things like cars. For instance, if you look at the latest generation of Tesla vehicles, they have 8 cameras, and many of the cameras are a combination of image cameras, also thermal cameras are coming deeper into play into automotive and to other industrial type of applications. In these sort of applications, one of the things that's very, very important is you need to have a very small enclosure subject to high heat. So you're going to have, if you put a camera in something like a car, you're going to be subjected to extreme swings in ambient temperatures and very long run times for some applications, maybe not in cars, as much as some things like smart city and industrial applications. But you have a very long run time requiring a very reliable electronics package, and you really can't use any active cooling in many of these systems. So these are the sort of requirements that our customers were telling about as we set forward on the path for a new generation of mid-range FPGAs. And what we came up with here is an aggregation of low power requirements, the need for higher performance that address various industrial communications, computing type of standards, and the smallest package size possible to address these particular markets. So we analyzed what our customers were asking us, and we made this as key components of a mid-range device that's basically modernized. That's basically taking these sort of requirements, removing the needs for active cooling, and really looking at high reliability to address this. And so what we have is our Lattice Avant. It's what we call a platform. It's based on 16 nanometer FinFET from TSMC, and it's a family of devices that share common components, that share common IP, that target various different end markets in different device and package combinations. We rolled out Avant about a year ago. We launched Avant in December of 2022, and our first device is what we call the Avant E, followed by the Avant G and X, and we'll talk about this in a slide or two. So what does Avant include? It has a 25 gigabit capable SERDES with a hardened PCIe Gen 4 controller. Also, it has a number of video standards and a number of standards that are associated with wireless and wired communications, such as JESD and CPRI and other Ethernet type standards. With the fabric, we use a 4-input LUT, and this is to get the lowest possible static power. And this is an area that we definitely excel at with the Avant product. And very plentiful, both DSP and embedded memory. So the ratio of DSPs and embedded memory to LUTs is very high in this family to address these target markets. For the external memory interfaces, what we're commonly seeing is the need for LPDDR4. So we have LPDDR4 as well as other DDR standards running up to 2400 megabits per second. And we use a hardened training layer, a hardened DDR5 layer for training, and then we use a soft memory controller behind that. We also add best-in-class security features into Avant. And here, areas that we're focusing on are both the bit stream and the user data encryption. And this includes algorithms for post-quantum. So as quantum computing gets more prevalent in the marketplace, they're more able to crack the most complicated code. So we include algorithms for post-quantum, as well as other common authentication and encryption standards in the security package. We have a wide range of different types of I/O, and we run up to 3.3 volt I/O and many other common standards. And far and away, we are the dominant leader in small form factors. So we can take this particular family in the packaging that's a tad under 100 millimeters squared. The three different families that we have in Avant are the Avant E, G, and X. So E has been out for 1 year, and we have many of our customers actively designing with the E product, and this includes the external memory interfaces, as well as the I/O interfaces and the E package. The E also includes the bitstream security package. And in December of this year, we're launching the G and X. So along with our developer conference, one of the major announcements is the rollout of the G and X devices, and they layer on the capabilities of the Avant E. And this includes SERDES support, up to 12.5 gig. So we support 10 gigabit Ethernet, we support PCIe Gen 3, and we also include a package of features for soft error detection and correction. And then with the X family, these products run up to 25 gigabit SERDES. And we also add PCIe Gen 4 with that speed, and the more advanced security features, including user security. So if you have a data set inside your FPGA that you want to use the crypto engine, you can address that with the Avant G family. For the tool set on Avant, we use our Radiant tool set along with Lattice Propel. Now, Radiant is a full-featured FPGA tool set that includes design entry. It includes compilers for the modern and standard languages such as System Verilog and SDC for timing constraints. There's a GUI package of floor planning. Then you have your compilers, and once you have the bit stream loaded into your FPGA, there's a tool package that we call Reveal, which is the debug capability. And basically what this is a in FPGA logic analyzer where you can select signals that you want to. There's a package to probe signals and show them in waveforms so that you can do in-chip debug. And we also have a nice GUI package to enable the various security features through the Radiant software. So if you need to do one of the bitstream encryption or authentication packages, or the user encryption or authentication packages, you can enable that through the Radiant software. The Propel is a IP integration tool that we offer, and this saves the user considerable time in integrating the different IP blocks onto an AXI bus. So for instance, if you have a RISC-V processor and a memory controller and I2Cs and various sensors and other integration blocks, this can all be done through the Propel tool set. And what it generates is the Verilog connectivity RTL, as well as all of the handoff package over to the Eclipse-based SDK that we use in conjunction with Propel. So it's everything that you need to do system level integration for both the hardware and the selection of IP, as well as the handoff of the memory map and features used in the IP so that a developer can use an Eclipse-based development for compilation and debug. Okay, now I'm going to hand it over to my colleague Mario, who will take over and discuss DP control and the torrential board.
Thank you, Larry. And I will try to be quick on this general purpose slide to pay more attention to what was our experience with the Lattice Avant in the design of the Tarantula board. Quickly introducing DP Control. DP Control is a company which is kind of a digital atelier where many custom designs can become products. Many customers of ours are mostly interested in some vertical, industrial, and civil, and different kind of even consumer grade applications where until a few years ago FPGAs were non-used at all, and instead we are demonstrating that it's possible to put video processing done in FPGA in commercial products. We are mostly active in robotics, industrial, IoT market, Edge AI, which was one of the key points in your discussion, Larry, and also in the vending, retail, and of course surveillance and ITS systems. We can go next slide, please. This is a bit of evolution of our company. We are starting 20 years ago, and it is like for us really an evolutionary process. We were coming from the old age up to today, passing through many evolution steps. And many of those were giving us the experience and in most cases the stressful experience in working with complex FPGA designs, which were setting a high bar in our expectation about new products. And this was exactly the challenge that we have been facing off when first seeing and discussing with Lattice about the possibility of integrating Avant in one product of ours. Next, please. There are three main pillars around our products and strategy. I will be mostly focusing about a real-world application of our IP cores. Most of our IP cores are dealing with images, and in this case, I will be discussing here in this presentation about the implementation on a Lattice Avant design of our ISP cores. Our ISP, we are talking about image signal processing, and ESPIDO is the collection of our IP cores totally devoted to efficient, compact, high-quality image processing to make what is coming out from image sensors, which is normally a known good perceivable image quality, into something that is absolutely stunning in terms of image quality for the human beings, or absolutely perfect in terms of algorithmic usage for machine vision application, which normally these two topics are in the common sense normally are matching. So we expect good algorithms coming out with good results out of good images. It's not exactly that way. So our strength is fine-tuning what is the final output of the image to process it in the most quality preserving way. We can go next. What is this mission? We are talking about using Avant and in general all the products which are in the Lattice line card, because we are normally users of Lattice components. But when phasing towards Avant, for the first time in our customer experience with Lattice product, we could have had the possibility of running on a mid-range FPGA, 16 nanometer technology, so expected to be fast enough to work with high resolution imaging and process a number of heterogeneous inputs, and at the same time delivering images in a number of heterogeneous outputs. So it's like discussing a MIMO system, multi-input, multi-output, where the input and outputs are as complex as an image sensor can be or a display output can be. Imaging is it's an environment which is rich of standards. MIPI is one of those, but it's not the only one. And there is a number of challenges when dealing with these different technologies for processing, transporting image data, doing the calculation, extracting information from metadata when it comes to artificial intelligence. There is a number of stars that must be aligned to give you the results you're looking for. And yes, okay, we accepted this challenge. We are talking about, yeah, Larry, you were saying 1 year ago, and I can say that we have been probably amongst the first users of Avant worldwide, if I'm not mistaken. And for sure, we have been the first in using this FPGA for a video application. We decided to make a multi-sensor board with up to 8 inputs and with a plethora of output systems, which could give a rich experience in managing image data or everything on the same FPGA. We can go next. This is the tarantula board. As you can see, it resembles a spider, then 8 legs, 8 sensors. And it's a prime time for us, honestly, to have such a gigantic amount of bandwidth, a gigantic amount of data being produced by all of these concurrent sensors attached to a single FPGA, and all managed with a peculiar aspect that we will see in the upcoming slides. And I don't want to disclose and make some spoilers before it is the right time. And in this configuration, you can see 8 cameras, 4K. The sensor was IMX334 by Sony. And our target was to design around Avant a real-time 1 pixel per clock eSpeedo instance per each image sensor in a concurrent way. And a rich set of output peripherals. We want output at the same time in a different way on HDMI, USB 3, and on a Raspberry Pi connector. The board is being available since February 2023, has been demonstrated in live at the Embedded World this year in Nuremberg, together with Lattice. It was a prime time for Avant, it was a prime time for our board. What is the peculiar point of this assembly? We also host a LPDDR4 memory, as Larry was pointing out before. Many video applications require frame buffer, require memory, and require hardened memory controllers, or at least easy-to-use memory controller. In our case, we were stressing ourselves to push the FPGA cells to their limits in terms of frequency and in terms of occupation. We urged ourselves to design the system without using that memory at all. So in practice, we are talking about having all of those 8 sensors running in parallel without a frame buffer. And only by using the 16 nanometer technology, we could achieve that result, running at a very high frequency. Details in the next slides, so we can go next. A first glance about what is the architecture of our system. We are talking about eSpeedo. eSpeedo is the collection of our image processing, pixel processing pipeline, and is a fully autonomous ISP running on Nexus and Avant families. It was coming on the Nexus first, of course, because the Nexus is a platform which has been available many years before Avant. But at the beginning of the Avant journey, we were immediately jumping on and implementing our eSpeedo also on the Avant technology. Our goal is to have up to Ultra HD resolution 4K and beyond 4K without any frame buffer operation. The diagram you see below is exactly what has been implemented on the board per each channel. So we're talking about 8 times this architecture. So here is per channel architecture. We have a MIPI input. We have our eSpeedo pixel processing pipeline. Then we have multiple output. Can be another image sensor mimicking interface like the CSI2 transmitter, or a DSI transmitter in case we are going to go directly on a monitor, HDMI display port with external components, or if this ISP is part of a bigger architecture, you can feed the output of the ISP directly in another bunch of IPs. So we also we are retaining the Axi4 streaming interface for the output. Per each channel, we have a separate RISC-V processor, which is talking continuously to the ISP in real time, running a very small but super hard real-time firmware, taking the statistics and running the AAA algorithms. One of the demo I was showing in Nuremberg on the Tarantula board was making one sensor totally blind and showing that all the others were not following in changing the parameters for the other sensors if I didn't want to. But if I wanted, this could have happened. In many multi-sensor systems, there is a master and many slaves, or you can have multi-master. Of course, multi-master systems are way more complex. We are talking here about a multi-master system with the possibility of switching to master-slave, all in the same architecture, just by reconfiguring or parameterizing, you name the word, the RISC-V processor. This was an extra bonus in terms of flexibility in this design. We can go next. Some more details about what is inside the SPIDO pixel processing pipeline. We have the complete set of tools which are required when it comes to making an image coming out from a sensor in a beautiful perceivable image for human beings, or as I told before, also for algorithmic usage. We can do defective pixel detection, removing the pixel which are not into the statistics. We have a very high quality debayering, which can work on a neighborhood of 7x7. So it's not a simple one. It requires lots of line buffer memory. And in this, Avant was extremely useful because of the topology of the new topology of the fabric. We were finding the memories exactly in the places we needed for having the maximum frequency not being being affected by any penalty, because our memory could have been in some other part of the floor plan. So the capabilities of the fabric were helping here in the physical implementation of the ISP itself. Then we have many operations which are common in other similar systems, like the color correction metrics, the color conversion for many color spaces, because in many cases human perceivable images are in RGB color space, but video compressors are working in the YOP or YCBCR or different color spaces. You need a color converter inside. So resides HDR, and this is another prime time for a memoryless ISP. You will see a dedicated slide for that in the upcoming ones. And everything is surrounded by XI-Light interface and XI-Stream for data. XI-Light for the configuration of parameters, setting all the ISPs, talking to between the RISC-V and the single parameter, and also managing external peripherals. In this diagram, not everything is depicted. There are many I2C slaves which are talking to sensors. We are monitoring external parameters. We are dealing with a number of other peripherals. Of course, you need a complex system. And in this, Propel system is absolutely helping in building up complex ecosystems with a very few mouse clicks. So designing a complex system is a few mouse clicks away from you when it comes with the right tools. Then we have the RISC-V with all the interrupt generation, gathering the statistics, and so on. All of these IPs can be synthesized with a programmable bit depth. So you can choose amongst having a fully fledged, let's say 14 bits, 12 bits, 10 bits, you can set according to your needs in terms of bit depth for the image processing, and then deciding at runtime how many of those bits you should use for matching the speed or matching the quality. You decide. If you have this decision, make a synthesis time, you can decide to save some space in the floor plan by reducing the overall size of the mathematical chains inside the ISP by propagating all the parameters around all the ISP itself. So the IP generation itself can be driven by customers' needs. And then there is a bypass mode when you want to debug what is directly coming out from the sensor. So as you can see, is a complex arrangement of 7 or 8 or 9, depending on the configuration, different IPs, which normally are provided in a bundle. Next slide, please. A few words about RISC-V. RISC-V is becoming ubiquitous in every heterogeneous architecture. Is the new common word when it comes into heterogeneous integration. In many systems, we are observing the integration of RISC-Vs, which are being deployed in billions units nowadays in a worldwide way. ASIC, FPGA, SSPs are full of these small processors, which are quite flexible and easy to use. In our case, in the case of Ispido, the RISC-V is the way we use our intelligent algorithms for reducing the workload for external MCU or MPU. In a few words, if you have a structure like this, you could drive the whole system by a microcontroller, or even not having at all a microcontroller, because the RISC-V itself can serve in configuring the IP, managing all the data transfers. In case you have a memory controller, this is not the case, but in case you have, managing the video DMAs for copying the data from the pipeline to the memory, from the memory to the pipeline back again, can be done in a single place and can be done in an homogeneous way, because the way you write the software for RISC-V is similar in many, many different architectures, and most of your code you can reuse in different designs. In our case, is also running the AAA algorithms in autonomous and per channel way. Next. A few numbers. What is our way of conceptualizing image processing? We think image processing must be a compact IP, a compact design, a compact set of primitives that should be small enough to be fitted efficiently in separate clock regions to avoid as much as possible that gigantic designs are affecting your maximum frequency. So the design must be a small ball in which the signal enters, the signal gets out exactly the way you want. It's not like a supermarket in which whatever is on the shelves you are putting in your shopping cart. This is not our approach. We are carving the IPs down to the bone, to the bare minimum is required, but with no compromises on quality. Here we are comparing the same image coming from the same sensor processed by a commercial ISP. I will not, of course, tell and disclose who is the supplier, but I can tell you only the sites, talking about a 90,000 lookup table and more than 3 megabits of block RAM used. On the other side, you will see the numbers of Ispido, 8,000 lookup tables, and the set of features is not comparable. So the leftmost is 8 bits as an output. We are taking instead and retaining the 12 bits input to output. And we have a full streaming operation, 1 pixel per clock. This allows Ispido to run at the same frequency of the sensor without getting the need of an external frame buffer. In total, including the RISC-V, we are in the league of 9.5K lookup tables. So it's 1/10 of the competition. In addition to that, the competition is brand locked and has some magic spells inside for tuning the AAA algorithms. Our code is fully inspectable by our customers. So there is also a concept of being opened, which is totally different from what you can find in the market nowadays. But apart from the marketing details, we can see in the next slide that there is something more that we can add because of the capabilities of Avant. Next, please. It was a prime time for us. We were able to fit HDR processing in an FPGA directly working on line buffers without any need of frame buffers. Avant was proven to be fast enough to process the data coming from 2 pixel processing pipelines in parallel to combine at the end of every line the new line into the HDR image. This is really an astonishing result, or better, the first time we have seen such a result in an FPGA, because we never had the chance of running that fast. Because in any case, even if you run fast and you have a memory at the end, you will be getting a one memory that must be shared amongst the various pipelines. So at the end, there will be some arbitration, there will be some network on chip, there will be some crossbar, which is setting the priorities between one pipeline and another. And apart not having gigantic buffers at the end of every pipeline, you cannot mix up the data coming from 2 separate pipelines in real time without the capabilities of an FPGA as performant as Avant. This allowed us to make a very small implementation of the HDR processor, which is only 900 lookup table, because it's the transfer function by itself, nothing more, that can run in real time directly at the end of 2 pipelines dealing with the DOL HDR sensors like Sony sensors. We can go next. This that looks like a European map, but it is not. At least this was my first impression when I've seen this picture, like also with the Mediterranean Sea on the bottom. It's the floor plan of 4 instances of our ISP on Avant. And here are the numbers I was anticipating before. We are topping 300 megahertz with a very narrow data path, 1 pixel per clock, and a full 8 core instances, which is capable to deal with 8 sensors 4K in a concurrent way, is using no more than 30% of a single Avant E500 device. And we are talking about having 8 independent image signal processors, giving you the maximum flexibility you can have in your mind. As I was anticipating before, it can work as a multi-master or can be in a master slave. The power numbers are also telling another interesting truth, that all of this system is giving an exceptional performance per watt ratio. And then we will see in the next slide. Here are a few numbers coming out from the mapping, so the placing route of Radiant tool, which was another nice surprise. Radiant was working in such a simple and immediate way for us. We were porting our design without getting acquainted at all with the new silicon. The tool was hiding all the complexity for us. It was a fantastic journey in approaching with Avant. The right tool chain can make your day when it comes to FPGA design. FPGA design done with the wrong tools can be extremely stressful, and this is a developer's word, so you can trust me, this is absolutely something that is not given for free in this business. And back to the numbers, we are talking we are getting here some interesting numbers. 4 cores that result in an even more compact structure are using 11% of the registers in this design and 12% of lookup tables. So we are in the league of 1/10 of the capabilities of this design, and we can manage 4 sensors 4K in real time. Next slide, please. Power consumption numbers. I will go straight to the point. The whole system is draining 6 watts, where 2 watts are only for the image sensors. So the FPGA, its power management, the surroundings, and USB 3 controller, and the HDMI controller, and other peripherals are draining no more than 4 watts in total. There is another exceptional number, which is the temperature. Temperature is the arch enemy of your image quality, because whenever temperature raises in such a system, the bias of your image sensors are it's affected by this temperature raise, and your image quality is severely affected. So keeping the temperature low in a video system is more than a desiderata, is a mission. It's a part of the design approach itself. The design must be taking into account thermals since the inception. I'm quite proud to say that the results we got on Avant with a fully streaming design was incredible in my observation on different kind of similar systems. We were not topping even the 60 degrees, is slightly below 58 degrees. It's a funny story around that. I don't know, Larry, may I tell a story to the audience? I think so.
Sure, yeah, we'd like to hear.
I was saying, I was showing off this design at the Embedded World in Nuremberg in February, and I was talking to customers, to interested customers, all the time, putting my finger on the top of the Avant design, their device, because I could, in many chances in our business, because first of all, it's a technical business. You are proud of what you did, and I was putting the finger on to show that the device was cool enough for me to host the finger without being burned. And I'm coming also from different FPGAs and different brands and different configurations, let me say this word. And I've never seen such a low thermal effect with such a workload running on. So congratulations, Larry. This is a fantastic achievement in the design of this device. It's a first time I see such a result in a real device. And small power consumption also has another side effect. It's good for the pocket. Simply put, your power management section is cheaper and smaller. That means you can make cheaper and smaller devices. Okay, so that's another nice part of the story. Next, please. Yeah, here there is a few parts of what we did to keep our design fast and cool. There are a number of design techniques which are coming from years of experience and years of evolution in the EDA market. And this is pairing with what I was saying before about the tools. Tool chains in EDA are normally not running as fast as the academic achievements are. And in most cases, the design strategies are made by the latest discoveries by academics. And sometimes you get frustrated because you know that you could achieve a result, but your tool is not supporting that strategy. And as a developer, this can be stressful, and it's showing you a potential results. It's a low-hanging fruit, and you are not capable to get it simply because your tool is putting between you and the result a barrier. I must say, in my personal opinion, but also it's a shared opinion amongst our developers team, FPGA team, that the tool chain by Lattice this time, the Radiant we are mostly talking about Radiant here. It was supporting all of these advanced design techniques without putting any obstacle in front of us. We were able to simulate and test gatings and resource sharing by having access to a very powerful synthesis tool, which is inside Radiant itself. All the IPs we were using were already optimized for the silicon device. So our learning curve about the IPs was not in any way steeper than what we already had for the previous generation of silicon devices like Nexus and even before. When it comes to pipelining and parallelism, streaming video application are the manifesto of these techniques. You cannot run any ISP without pipelining everything. And the level of visibility we got around our Verilog and system Verilog sources and analyzing all of the unit systems for checking if the synthesizer was exactly doing what it was written in the HDL. It was a fine and non-stressful journey. In many cases, choosing your memory topology can set the points in two working systems, but one is faster and another one is not. I was saying before, the topology of the memory is crucial when it comes to manage with large line buffers, like in the case of HDR. Well, I must say that the floor plan in Avant and all the fabric structure was smartly designed, and we were finding the memories exactly in the places where we needed. DSPs were exactly where we needed, and clock distribution primitives were exactly where we needed. So in terms of optimization efforts, I can't say it was a push button, but almost a push button effect. So we were setting the stage, running the synthesis, fine tuning the place and route. Normally in this process, you have a 30, 30, 40 in terms of percentage of time you spend. Probably computer scientists can say is 90% optimization and 10% design. In EDA is slightly different. We spent really no more than 20% of our time in making the fine graining optimization. And it's quite an achievement. I'm running a team as a manager, I can say was also an economic achievement. So having less persons involved into the final optimization of an IP and the design has positively affected also our financials. That is not an irrelevant topic these days. Asynchronous interfaces, just to set the last word, all of our systems are all based upon the XI abstraction, and we are clock agnostic. In this case, you can manage the interconnection between IP cores in an almost seamless way, because you make no assumption in what is running on the boundaries of the interfaces. This can cost you some extra memories. Back again to the point about the selective memory usage, those memories were already well positioned inside the floor plan, so it was a minor effort for us. In the end, we were reducing the dynamic power of the design because we were using the right primitives in the proper way. I think I'm done. So back to you, Larry.
Great, thanks. Appreciate that. Let me ask you. So we started looking at first silicon around August of 22, and you were already demonstrating a completed board for what first quarter of Embedded World in
February
23. So February, that's crazy. Like, so that's only about 6 months since you had. How long did you actually have the parts before you were able to do such a demonstration?
I must say that let me do some marketing. I have a fantastic team. Okay, so but nevertheless, you know, you are in this business much longer than me. If a silicon device is not ready for the prime time, you can't deliver in 6 months.
Right.
We are talking about an absolute truth. For such a complex design, it's impossible to deliver in 6 months if the tools are not helping, if the silicon is not ready, if your working experience is not pleasant. There is so many stars to get aligned that normally you are missing the delivery dates. I'm proud to say that our board was ready before Christmas 2022. We spent January and beginning of February in the fine tuning, and you cannot believe in 3D printing the case. That was the longest part of our design because we are not in that business. So, but electronics and assembling and bringing up the board, I can never forget the bring up of the Tarantula board was taking for us 1 week in total, 3 persons.
Wow. Impressive.
Yeah,
And now, sorry, so tell me a little bit about some applications where you could use such a system.
Yeah, it's interesting. There are a few emergent applications. The obvious ones are in surveillance. Smart city and surveillance require as many eyes you can put on the field. And multi-view systems are especially useful in urban concepts in which you have so many crossings and you want to check traffic, just to give you a typical application, and increasing the resolution because you want to do pattern matching, AI, license plate recognition, speed ticketing, all kind of applications you can think in an urban context.
Right.
You need an image. And multi-view systems are crucial. There is a number of other applications in industry when it comes to monitoring industrial machinery. In that case, can be a mix between many eyes or probably not so many eyes, but higher frequency, higher frame rate. You know that there is a balance. Is normally the capabilities of these systems are not only bound by how many interfaces you have for input output, but the total bandwidth of the system. So running a 4K sensor, 30 frames per second, you could, and running 8 of those, there could be a customer interested in running 4 of those double the speed, or running 2 of those 4 times the speed. So an FPGA like Avant is incredibly useful if you are good enough in mixing up all of these factors and giving more options to your customers. In many cases, customers are coming to the FPGA suppliers. In this case, customers could be interested into a new product like Avant simply because they can't solve existing problems with the hardware they have. So here, the point is catching up with some requirements. We are getting inquiries for the Tarantula from avionics customers. And it's quite strange. We never got such an inquiry before the Tarantula, and we got such a contact. What I can say more, so recapping, smart city industry, now there is avionics, and in general, all of those applications in which you can mix up the speed versus the resolution, and you have a flexible solution.
Excellent. All right. Well, thanks for sharing. So again, what we've shown is one of the early users of Avant with a very interesting and successful rollout here. If you're interested in utilizing DP control, right, reach out to them and they might be your next design services partner. All right, so if you have additional questions for Lattice or for DP control, we'll use this time to answer any questions, and we appreciate your attention.